And any questions on anything at all up to now? All right. Appreciate you getting your paper in. I'm recording this here so others will hear that. Finally, I got one paper from this class, and that's good to see. So the rest of you get yours in. You have just 2 more days in January to take advantage of the 4 bonus points, but try to get that done. Now, I have my mark on example 8 on page 20. Is that where you are? Oh, okay. We'll go from there then. Let me get the slideshow set up. Current slide. Okay. Yeah, we're projecting now. Solve this system of linear equations. Oops, let me get my pen activated. All right. 2x1, that's x sub 1, plus 4x sub 2 minus 2x sub 3 is equal to 1. Second equation, 3x sub 1 plus 5x sub 2, and that's also, no, I'm sorry, the first one's equal to 0, this one's equal to 1. Make sure I got the numbers right. Okay, I think we're going to double the class size. Okay, good deal. Nigel's here. And Nigel, there was one new announcement today. I won't go over the rest of them, but coming up Wednesday, I'm not sure you can go to it, but you might know someone who can go to it. Have you heard about Lady Day? It's a Red Mountain Theater production, so it's pretty professionally done. Lady Day at Emerson's Bar and Grill, and it's about Billie Holiday, her last performance at this seedy bar in Philadelphia shortly before she died. Somewhat R-rated, so don't let that draw you, or it may keep you away, but don't let it draw you. It's presented for Lawson State. The college is paying for it, and that's, I think, a pretty hefty payment too. It's day after tomorrow, Wednesday, February 1st, 1 o'clock in the afternoon. Can you do that? No, I didn't think you could, okay. But you may know of someone who can. A.G. Gasson Auditorium on the Birmingham East Campus, across from Winona, on the East Campus, and it is for mature audiences. So if you want to read more about it, I've got it here. So, got your mark. All right, we're just starting example 8 on about the middle of page 20, okay? Now, anything strike you about the system of equations? Okay. One thing that I note, of course I'm used to looking at this kind of thing, we have 3 variables, only 2 equations. There's no way that this is going to come up with a unique solution. I don't think there's any way that's going to happen. You basically have to have at least as many equations as you have unknowns in order to get a unique solution. Now, just having that doesn't guarantee you a unique solution either, but it's absolutely required for you to have that. So what would we do with this? Where would you go? What would be your step 1? Say again? Matrix. We call it an augmented matrix. And how would that go? 2, 4, -2, 0, 3, 5, 0, 1. Okay. Now, frankly, another thing I noted about it, and I was going to see if any of you did, first equation to me is a little ridiculous. Why? Yeah, it's everything's multiplied by 2 unnecessarily, but that's really our first step. What do we want to happen? A 1 in the upper left. How can we make that happen? Divide the first equation by 2. Now, we'd have to do that whether the other coefficients were even or not. We'd still have to do it. We'd have some fractional coefficients, some halves or whatever in there. But this one, There is really no reason to even have those in there because you can divide everything by 2 and not change that and still have integral coefficients. So let's move on from there. So that's what we're going to do. Row 1 divided by 2 is the new row 1. Okay? So what would that give us? 1, 2, buckle my shoe. No, never mind. Go ahead. I broke your train of thought. Okay. -1. 0. Okay. And we just write down the second row because we're not doing anything to that. 3, 5, 0, 1. That's one thing about matrices. They simplify in many ways, but then there's so much writing that you have to do, copying down rows you're not using at the time, but necessary to do. Keeping up with the paperwork. Okay? Next, what do we want? 0 under that leading 1. And how do we make that happen? Top row by -3 times row 1. Add it to row 2. Okay? And since we're using row 1, here again, we just copy it down. 1, 2, -1, 0. And what's in new row 2? 0. -1. A little louder. 3. Excellent. And 1. Okay. What's the next thing that we want to happen? Say that again. Yes, we're leading coefficient of row 2. We want to be a 1, but it's a -1. How do we make that happen? Multiply by -1. So guess what I'm going to do? I'm going -1 row 2. Okay? I'm just going to leave it like that. And guess how I'm going to do that? Watch me. Oh! Increase class size by 50%. All right. Marcus is here. Both of the Williams brothers are here. Where are the others? Never mind. Okay. Now, watch me multiply that by -1. That was nice, wasn't it? Okay? All you have to do is change signs of that bottom row. Now, guess what kind of elimination we want to do here? What form we want to wind up in? There's 2 ways to ask the same questions. Do we want Gauss elimination? I think we want Gauss-Jordan elimination. What does that entail? Yes, not only the numbers below leading 1s need to be zeros, but numbers above leading 1s need to be 0. So what will that affect? What will need to be changed? That 2 needs to become a 0. So how do we make that happen? Yep. -2 row 2 and add it to row 1. Excellent. Okay. So we're using row 2, so write it down. 0, 1, -3, -1. Now, time out just a moment here. Just letting you know you don't have to do the same order all the time. When that was still a -1, you could have taken this, multiplied 2 times row 2 and add to row 1 before you change signs. That would have also given you a 0 there, and then you could have changed signs. It didn't matter which order we did that. But you just have to be very careful when you change order, okay? You're not going to mess something up. So what does this give you? 1, 0. Say again? little louder. 5, that's what I saw. Okay, next. Say again. Say again.
Oh, no. That's
2. Okay. Very good. All right. Now comes the crucial point. You know, it's nice when all the coefficients, all the variables wind up with a coefficient of 1, and everything else is 0 except that last column, and then it's just easy to write down the answer. Can't do it here. But I want you to tell me what this bottom row represents now. Thinking back from whence it came. Okay, 0x1, I'm going to leave that off. Okay, x2 minus 3x3 is equal to -1. That's exactly what that stands for. Okay? Now, here's how we proceed with something like this. These leading ones are going to enable us to at least come up with an expression for x2 and x1. We're not going to be able to identify x3 at all. So we're going to make it what we call a parameter. And the book's favorite parameter, for some reason, and it may be true in all of linear algebra, but this book especially, is t. T for 2, I don't know. So let's let x3, and that's going to be the first thing we're going to do, is let x3 equal t. It's going to be a parameter. It was a variable, it's now a parameter. What's the difference? Really minor, but we're going to do that. With that in mind, then, what does this new second equation become? What does it become? x2 minus 3t equal to -1. Let's solve that for x2. How would you do that? Add 3t to both sides, and that would give us x2 is equal to, I kind of like to lead with the positive, 3t minus 1. You could say -1 plus 3t. It doesn't matter, right? Okay, so I'm going to write that down. Then, this looks like it's going backwards, and it kind of is. x2 is equal to 3t minus 1. All right, tell me what that first equation is saying now. The first row of your matrix, what does that tell you? What equation does that relate to? To what equation does that relate? Or something like that. x1 a little louder. Yeah, 0x2. Okay. How'd you get that? Okay. Plus 5 what? T. Excellent. Okay. Is equal to 2. And what are we going to do with that? Solve for x1. And what does that give us? What do we do with it? When we solve for x1, subtract 5t from both sides. And that gives us an x1, because these go out, okay? Just like these went out, okay? x1 is equal to 2 minus 5t. Very good. Guess what we have now? We have an ordered triplet, and that ordered triplet comprises of x1, which is 2 minus 5t, x2, which is 3t minus 1, and x3, which is t. Okay, there's our solution, only it's not just a solution. How many is it? An infinite number of solutions. Why? Because you can choose any t in the world. How about t equals 0? What would that give you as a solution? 2, -1, 0. Okay? Give me another t. 1. Wait, okay. I'm going to put the 1 here because that's a t. Okay? What would that give you? -3. 2, you said? Yeah. There's another one. There's an infinite number of them. Can we check them all? No. Okay. We'll just leave it like that. That is our solution. 2 minus 5t, 3t minus 1, t. That is our family of solutions. Infinite number of them. Okay? If you think back when we were dealing in two-space, 2 equations, 2 unknowns, what were the 3 possibilities on your solutions? What would that give you? A single solution, that point of intersection. What would that give you? No solutions, never happen. And what was the third possibility? Infinite number of solutions. That's equivalent to what we have here. Infinite number of solutions. And frankly, folks, anytime you have more variables than you do equations, you know you're going to wind up with an infinite number of solutions. Oh, no, that's not quite true. You may wind up with no solution, okay? If when you did whatever steps you're going to do, you wind up here with a, look at this now, a 0, 0, 0, -1, guess what that is? 0, 0, 0, -1. No solution. Okay, so just because you have fewer equations than you have unknowns or more unknowns than you have equations doesn't guarantee you an infinite number, but if you have a solution, if it's a consistent system, it will be a dependent system. Infinite number of solutions. Okay? And for every t you can choose, so if t is any real number, that's going to give you a different solution. Okay? Now, in this case, if you were to plot those, which is sort of hard to do, let's see if we can think of that. Let's see, how do I do it? Yeah. 2 on the x-axis, that right there. -1 on y, that's going back into the mechanical room there, 1 block. And then stay right there on the floor, okay? That would be 2, -1, 0. And then on the next one, -3, this isn't very good. That's 3 blocks out into the air out there. 2 blocks on y, okay, somewhere here, and then up 1. So from that point to somewhere back there, every point you would choose then from there on, you're going to find on that straight line, okay? But that's neither here nor there. Well, it's somewhere, but not. Anyway. Okay. Let's see what they got. 2 minus 5t. They said minus 1 plus 3t. T. Yeah, that's your solution. Okay. You place an arbitrary parameter for every every variable with a non-leading 0. And you could have had more than one. Now we're going to jump to another concept, and we sort of hit this in the discovery we did at the end of last class, and that's this. Let me erase. Anyone needs this any longer? Okay. You say, please get it off of there. We're sick of hearing you talk about it. Is that what you said? Okay, never mind. All right. Let's come up with a system of equations. A generic system. A11 x1 plus A12 x2 plus A13 x3 plus dot, dot, dot. We love these dot, dot, dots, don't we? Plus A1, and is it n they're using? Yeah, n x sub n equals 0. Okay? A21 x1 plus A22 x2 plus A23 x3 plus dot, dot, dot plus, guess what that one's going to be? A sub 2 n x sub n. And that's going to be equal to 0. Okay? And then we're going to dot, dot, dot down the ways further until we get to the mth row. And that would be a m1 times x sub 1 plus what's next? What's next? We're on the mth row, so that would be a m2 x2 plus, tell me, a sub m3 x sub 3 plus, I'll get these dot, dot, dot. Okay, next, a sub m n x sub n. And that's also equals 0. And we dot, dot, dot those, and we dot, dot, dot those, we dot, dot, dot everywhere, dot, dot. Okay. All right. And you can do all sorts of other dot, dots if you want to, that way and this way and every way. Okay. So you got all sorts of things there. Now, this system of equations has a specific classification, a name for this. Anyone remember my saying it or know what that is? What's the key here? What looks different from this system of equations from others we've done? All zeros for your constant terms. You're absolutely correct. I sometimes call that the solution vector. You know, what all these things are equal to, they're all zeros. Now, based on what we did right at the end of class last time, this lets you know one fact. It's not a very earth-shattering fact, but you do know. And the question, I guess I'll phrase it this way, is that a consistent system? Now, remind me what's the difference between being consistent and inconsistent. Consistent system is guaranteed to have at least one solution. An inconsistent system is guaranteed to have no solutions. Okay? Now, a consistent system may have more than one solution, but inconsistent system can have no solutions. A consistent system is guaranteed to have at least one. So which would you classify this? Can you tell just looking at it, without doing any row reductions or anything else, what that system is? Consistent or inconsistent? Say again? Consistent. Why? And which one is that? Can you name me a solution? To say it's consistent, you got to give me at least one solution. It's going to be an ordered n-tuplet, and that solution will be 0, 0, 0, dot, 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 0, where you have n zeros there. Will that work? Absolutely. If you put all the x's, all the variables equal to 0, 0, 0, 0, 0. Every term on the left-hand side is 0 for every one of these. And we already know that all the terms on the right-hand side, the only term there, is a 0. So you're guaranteed, and that has a special name, this solution. Not a very complimentary name. What do we call that solution? don't go calling your friends this, the trivial solution. It's this, well, in a homogeneous system, the trivial solution, all zeros for your variables, that is always a solution. So every homogeneous system is consistent. Okay? Now, the issue is, are there any non-zeros solutions? That's where the fun comes in. Okay? But we know that's a consistent system because it has at least one solution, and that's the trivial solution. The question is, does it have any others? Okay? That's called a homogeneous solution. And the other name other than trivial, maybe trivial is a two, is obvious solution, which I wasn't sure it was all that obvious, but hopefully it is now, right? Okay. So let's do one. Can we go and erase this one in case we need more room? Okay. All right. This is example 9. X sub 1 minus x sub 2 plus 3x sub 3. Guess what that's going to be equal? 0. We're doing a homogeneous system. 2x sub 1 plus x sub 2 plus 3x sub 3. What will that equal? 0. Yeah, because they told us ahead of time it's a homogeneous system. Now, actually, it said just solve the system, but the title of that was solving a homogeneous system of linear equations. Why is that a system of linear equations? Just a little bit of review here. The variables for all the exponents are 1. You don't see any exponents, meaning they're all 1s. Can't have any negative exponents, can't have any fractional exponents, can't have any exponents greater than 1, like 2, 3, or 4. None of that. Okay? Yeah, that's a linear system. Okay. Now, what would you choose? How would you choose to solve that system of what else can you tell me? Just looking at that, any other conclusions give me any conclusion you can make about that system. Is it consistent or non-consistent? Inconsistent. It is consistent. Why? It has at least one solution. And what is that solution? 0, 0, 0. 0 for x1, 0 for x2, 0 for x3. That guarantees both those equations are going to equal 0. Yes, it has a solution. So this is not going to be a no-solution problem. But what's the other thing you notice about this? More variables than it has equations. And with a homogeneous system that everything's equal to 0, there's no way you're going to find what our no-solution case is. Remember what that would be? Once we got it into a matrix, it would be 0, 0, 0, something not 0. Anything not 0. Negative 1, 1, 2/3, whatever. If it's not 0, that would be no solution. But can you ever make that last? No. Everything you do to that, exchanging 2 rows, adding a multiple of one row to another, multiplying or dividing by any non-zero entry, those are always going to stay 0. So you'll never have the case. You may wind up with 0, 0, 0, 0, which is never, and even if you came up with 0, 1, 5, 0, that's still a solution. It's only when you had 0, 0, 0, non-zero, would it be no solution. So this will guarantee to have not just one solution, but an infinite number of solutions. How would you proceed to show that? I already gave it away. Yes, 1, negative 1, 3, 0. Okay, next. 2, 1, 3, 0. And what will you do with that? What do you want to happen? What do you want the first thing to be? 1 in the upper left, we already got it without doing anything but writing it down. Good for you. You're being very efficient today. Next. Yes, you want the thing beneath that leading 0, the 2, to become a 0. How do we make that happen? negative 2, row 1, plus row 2. Got it. Okay? And since we're using row 1, we have to write it down. 1 minus 1, 3, 0. Okay. Next. Zero, 3, a little louder. I couldn't hear. Negative 3. Okay, I'll buy that. I won't pay too much. And what? 0. Okay. I'm liking that pretty much. Why do I especially like that? What's the next thing we want to do? The leading non-zero entry in the second row to be a 1. How do we make that happen? Divide by 3. So we have to divide the whole row by 3. So row 3 divided by 3. That's what we're going to do next. I'm going to try to squeeze it in here. Again, we're not using row 1, so I'm going to write it down. 1 minus 1, 3, 0. New row 3 will be, row 2 will be 0, 1, negative 1, 0. What's next? We got our leading non-zero entry of the first row to be a 1. We got a 0 below it. Already, with what we just did, we got the leading non-zero entry in the second row to be a 1, but now we want, there's nothing below it, so we want what's above it to be a 0. Okay, and remember, this process is called, it's Gauss-Jordan elimination. There's another term for it. I didn't mention that last time. I said there were 2 terms, so I didn't come back and tell you the second one. The first way with Gauss elimination, we're only getting it into row echelon form. In Gauss-Jordan elimination, we're getting it to reduced row echelon form. So that means we want what to happen? That negative 1 to be a 0. How do we make that happen? Row 2 plus row 1 is the new row 1. Okay? So that will become, what's our new row 1? 1, 0, 2, 0. See, nothing we can do to change that last column of zeros, okay? And what do we do with row 2? Trick question. Write it down, okay? 0, 1, negative 1, 0. We've got it in reduced row echelon form. We've done our Gauss-Jordan elimination. What do we do now? Basically interpret. What does that last row tell us? x2 minus x3 equal to 0. And what's our little trick here? Yes, and we usually choose the one without a leading 1, so that's going to leave it x3, and we're going to make that t or any parameter other than x that you want to choose, okay? X would work, but it would be confusing. All right, so already by doing that, we've said let x3 equal t, okay? Then what does this second equation tell us then? x2 minus t is equal to 0. Then what would we do? Yeah, add t to both sides. And that gives us then x2 is equal to t also. Okay? Boy, this is getting boring, isn't it? Never mind. You would never say that. Okay? Now, what? So first equation tell you x1 plus 2t equals 0. And what does that tell us? What would you do? Solve for x1. What would that give you? Yes, x1 is equal to, what did you say? Negative 2t. All I heard was negative 2. I want to make sure. So what's our ordered triplet as that represents our solution? Negative 2t, t, t. Okay, but not on the floor. Okay. Now, give me some values. Give me one point that would solve. 0, yeah, 0, 0, 0, obviously did. We didn't write it down, so let's do it. So you see, the trivial solution does indeed work, okay? We knew that from the beginning. Give me another one. Okay, what about 1? T is equal to 1? So what would be your solution then? Negative 2. What? 1, 1. Or you could have done 2, negative 1, negative 1. Or any other t you want to choose. Any real number t, fractions, decimal, rational, irrational, doesn't matter. Put it in there. Negative 2 pi, pi, pi. Okay? That would be a solution. Negative 2 e. Sounds like it's all a mouse. Okay? That would work. Okay? Negative 2 square root of 15. Square root of 15, square root of 15. That would work. Yeah, it's an infinite number of solutions there for that one. See how they got it? x1 equal negative 2t, x2 equal t, x3 equal t. Has infinitely many solutions, one of which is indeed the trivial solution. Okay? That then leads to a theorem. Okay? Let's jot this one down. All right, to erase it? Everybody through? Not yet? You got it? Okay. All right. Theorem 1.1 in this section. Number of solutions of a homogeneous system. I bet you can tell me what to write here. I'll write down part of the first line. Every homogeneous system, writing this a little better than normal, of linear equations, except our linear equations, I'm going to start abbreviating some, I'm tired of writing, is blank. What would fill in that blank? Every system of linear equations is what? Say again? Consistent. You're absolutely right. We didn't need the theorem. You knew it already. Moreover, if the system, now they made a jump here, if the system, we didn't say this, but we're going to, has fewer, we haven't gone this way yet, but I think we can do it, equations than variables. No, we have. This is what we've been doing. Thought they were going to say variables and equations. Has fewer equations than variables. We have done this. Okay? Then what can you conclude from that? It must have blank solutions. Actually, blank solutions. And it's a number. Say again? Infinitely many. Okay? Infinitely many. Okay. We've already shown that. To prove theorem 1.1, use a procedure in example 9 that we just did. Go through and do it, and guess what? We finished 1.2. Finally, okay. Homework exercises here for 1. Any questions on 1.2? Okay. Homework exercises, any of the odds 1 through 5, you've heard that several times. Either 7 or 9, you've heard that several times. Those are easy. Any of the odds 11 through 17. Any of the odds 19 to 23. Any of the odds 25 to 29. No, I'm sorry, 25 through 37. And they say you might need a software package, but if you can do some of it or at least set it up and start thinking about it, try number 39. If you get too bogged down and don't have a software package or a graphing calculator, you don't have to spend hours on this, but think through what you would do. Okay, either 41 or 43, or both, by the way. There's a very good applied problem, number 45. Then try to do 47, 49, 51, 53, and then the rest of these are sort of think through deals. I would definitely give them a thought or two, and that would be 55. There's a true false 57. Don't expect to see many of those on the test, so you may have a question. Is it yes or no? You could have something similar, but it'll usually entail something more. Think through 59, 61, 63, and by the way, 63, I'm going to give you a heads up here. You have heard in the earlier part talking about what we're going to be doing in the class, and it may be something, when I said it, it was blah, blah, blah. But what we're going to be doing, if we can get that far, in Chapter 7, is eigenvalues and eigenvectors. Number 63 is basically preparing you for that situation. The lambda is typically called your eigenvalue, and we haven't mentioned what the eigenvector is yet, but that leads to it, okay? Then you can look at either 65 or 67 or both, okay? Again, those are just think through type problems. You don't really have to do anything except make sure you understand what's going on with them and what you would do if you were ever asked to do that. I'm probably not going to ask you to do that, but in case in an upper level course you might be hit something like that, what would you do? How would you proceed? Why is this not staying on? There we go. All right. So let's move on to 1.3. Systems of linear equations arise in a wide variety of applications. In this section, you'll look at two applications, and you will see more than one. You see more in subsequent chapters. I'm not going to dwell on this because this is really more about systems of linear equations, though it does use matrices to solve them. And that's the whole point of this. But this chapter is more on systems of linear equations. The only reason we've done anything in it is because what we're trying to get to is matrices, and we've been doing that. But polynomial curve fitting. And in your book, you'll see that. And what can you immediately tell me about the equation that represents? It's not a... Okay, yes, it has multiple powers. That has at least a power of 3, maybe more, for at least one of the variables. Well, yeah. Okay, so yeah, not a linear equation. That's what I was getting at. So why is that being mentioned here? Well, if you have certain points on that polynomial equation, you can then fit a curve to that. And guess what? The curve fitting process does give you a system of linear equations. It's a sneaky technique. It's a trick, okay? What you do is sort of let your variable be your variable to a power, okay? For instance, if you plug in, let's suppose that n points on the xy plane
x of 1, x of 2, x of 1, y sub 1, x of 1, x of 2, y sub 2, x of n, y sub n. Endpoints on the xy plane, okay? Represent a collection of data you're asked to fit a polynomial function of degree n minus 1, okay? So in other words, you have n points, but you want to fit it to a polynomial degree n minus 1. Well, then you know that p of x is going to be a sub 0 plus a sub 0x plus a sub 0x squared plus a sub 0x cubed, a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus on and on till you get to a sub n minus 1, x sub n minus 1. That's your polynomial equation that you're trying to fit those endpoints to that n minus 1 degree equation. What do? If you have those n points, plug them in, okay? The first one is going to be that equation is equal to y1. That equation for x2 is going to be y2. That equation for x3 will be y3. That equation. So you see now your variables are your powers of x. Okay? Not a nonlinear equation. This is a system of linear equation. You can use a matrix to solve that system of equations. You have n equations with n minus 1 coefficients, right? A sub 0, a sub 1, a sub so when you get to n minus 1, because you have the a sub 0 here, when you get to a sub n minus 1, that gives you a total of n equations. N equations and unknowns, if that's a curve, you know you got a solution. Okay? So, that's polynomial curve fitting. Now, do any of you think you're really going to need that in a future course, or you don't have a clue whether you would or not? Well, if you do, go back and check here. Okay? And they give a couple examples on it. And then they talk about translating large x values before curve fitting. And that's another technique. What if your x of 1 are years? 2006, 2007, 2008, 2009, 2010, you know, and you have some value for each of those, like your net profit or something else like that. Well, guess what? Do you want to do all your calculations by raising that year to the second, third, fourth, fifth power, fourth power, whatever? No, okay. So you use a surrogate and maybe 6, 7, 8, 9, 10, rather than 2006, 2007. Yeah, it's going to be fine, just a year after that. Or you could use, that would be the year after 2000. Or what they chose is that middle one, 2008, and do that to be your 0, and then have a 2007 be minus 1, 2006 to be minus 2, 2009 to be 1, and 2010 to be 2. You can choose your, it's just called scaling. That's all you're doing is scaling your variables, okay? For instance, if that was your net profit, your business has made millions of dollars that profit that year, don't you wish, you know, then you could just write it in how many million? 1.2 million, 3.5 million, you know, you could do that. Scale on either of those, okay? And they have another application of curve fitting. This is the astronomical one, so sort of fun if you're into astronomy. Okay, there is a linear algebra applied here. Researchers in Italy studied the acoustic noise level from vehicular traffic at a busy three-way intersection on a college campus. They used the system of linear equations to model the traffic flow at the intersection. Okay? This is a real-life problem. You could go find that source, if you can, and do your paper on that if you like. Which leads to a concept called network analysis. Okay? And again, you use matrices to solve these.
just like you did in the others. But you see in the book, they just said, use a matrix, here's your solution. Okay. Thank you very much. Okay. This one, they actually show it, so I think I will do that one. Okay. This is example 5 on page 29. And I'll try to represent this. However, now, some of you may think network, and you might think we were talking about electrical network. Not necessarily. It could be any kind of a network, like a traffic flow problem. Okay, that's a network. So here's what we have. We have, and I like to call these nodes. Okay, node 1, node 2, node 3, node 4, and node 5. Okay, and in between the nodes we have paths. At least I call them nodes. Let's see. This is a network. Okay. Oh, they call them junctions, which any of you had Dr. Bryant's Cal 2, okay, and you had Kirchhoff's rules, junctions, right, and circuit and currents. Same thing. That's exactly what this is. This is a rather strange one electrically, but this is that kind of problem. Junctions and what do they let the other thing represent? They don't give it a name. I'll call it pathway. To me, that covers electrical or streets or whatever you want to do. Neural pathways, anything such as that. All right. Between 2 and 1, we have a path going from 2 to 1, and its volume of traffic, whatever, current, whatever you want to call it, is 20. Okay? You have another path going from 1 to 3, and we don't know that one. That's x of 2. I should have started with x of 1. Oh, there we go. 1 to 4, that was x of 1. Okay? 2 to 3, that's x of 3. From 5 to 2, that's x of 4. And from 4 to 5, we have our x of 5. Have we left out anything? Well, sure we have. From 3 to 4 and going in that direction, we know that's 10. And from 3 to 5, we know that one also is 10. Okay? So what do we have here? Well, just looking at that, you have 5 unknowns. Now, looking at that also, we know that we have 5 nodes, or junctions. And you have a whole bunch of pathways. We have the 5 unknown plus 3 known. So we have a total of 8 pathways. 3 around 3 and 4 around 3 and 4 around the perimeter, not touching 3. So 8 pathways, but some of those are known and some are not known. Okay? So, what we would do, what would Kirchhoff's junction law tell us to do? Measure all the inputs and output at a given junction. Let's start at equation 1. What's going on at equation 1? Now wait a minute. The problem set us up with arrows here. Okay? They're being really nice. Okay? It could be that all you knew was the arrows for 20 and the 2 tens. Those are the only ones you knew for certain because you had measured those. The rest of them you don't have a clue. So you put the arrows in anywhere you want to, any direction you want to. You just have to have all the pathways there. If you guess wrong, you're going to wind up with a negative. Then you know the arrow went the other way. So it doesn't really matter which way the arrow is going, but set up your equations according to what it says. And what does this tell you? At junction 1, Okay, I guess I need to back up here too. Here's what Kirchhoff's rule says, law, okay, on junction law, is that and he's talking about electricity, the current coming into a junction has to equal the current going out of a junction, right? That makes sense, right? Any kind of a system that you have here, any kind of a network, you can't get more out than you put in. It has to equal. So what do we have going out of this junction? Junction 1. Going out we have X1 what else you have going out of? Plus X2, right? They're both going out. What's coming in? 20. So that has to equal 20. What goes out has to come in. Okay? So that's up. Let's go to junction 2. All right? Now, in order to keep things, okay, let's look ahead a little bit. Remember what we want? Our systems of equations, you want variables under variables, equal signs under equal signs, and constants under constants. Remember? Okay. So we're going to set up our equations to make sure that happens. So when I look at example, at node 2 here, okay, junction 2 here, I see X3 going out, X4 coming in, and 20 going out. Okay, now I can write that in any number of ways, but how I want it to wind up is looking like this. Okay, so you want X3 going out to be a plus or a minus. I don't care, I really do, but what would you like it to be? Plus? Okay, I like that too. Thank you very much. So that's X3 going out, so that's a plus. So that would make X4 minus X4, because that's coming in. So that's the net going out, right? And what's the net coming in? Negative 20, because it's going out. Now you could have also written this way, if you prefer. X3 is the out, no, X3 plus 20, those are out, is equal to X4 coming in. But then rearrange it to get it to look like this. And what I just said, write it down. X3 plus 20, that's going out, is equal to coming in X4. So I want it to look like this, so I'm going to subtract 20 from both sides and subtract X4 from both sides. That gives me exactly what we've got there. Okay? So you can do this step and then get that answer, or now when you get really complicated, you might want to keep it simple. I'm not going to say the next word, but just go from there. Okay, let's go to junction 3. What can junction 3 tell us? You tell me. Okay, he wants to use a negative x. That's perfectly fine, as long as you stay consistent with that. Negative x2 minus x3. He's staying consistent so far. Say again? Is equal to negative 20. He stayed consistent. Now, frankly, I would have said that that's coming in equals that that's going out. That's x2 plus x3 is equal to 20. Same thing, just multiply through 1 minus 1. Same thing. So however you want to do it is fine, as long as you're right. Okay, as long as you are consistent with what you're doing. Okay, so that was node or junction 3. How about junction 4? What does that tell us? X1 minus X5 equal negative 10. Okay. You like leading with a positive, which I like too.
You got x1 coming in, but x5 is going out, so they have to have opposite signs. So that's the net coming in, net going out. This is coming in too, so that's going to be a negative 10. Or you can do it this way, x1 plus 10 is equal to x5, and then manipulate like you did here. You'll get that same answer.
Okay, that was junction 4. How about junction 5? What do we have there? You tell me. You said negative x4? That's fine. Plus x5? That's fine. As long as you are consistent. Negative 10 equal negative 10. I probably would have done it the other way, but it's perfectly fine. X4 is going up, minus x5 is coming in. Or minus x5 is going out, okay? Because that's coming in, so it's minus that. Okay? So the going out, so on this side, coming in on that side, I would have just, but it doesn't matter. It really doesn't, as long as you're consistent with that equation. All right, guess what's the next thing we're going to do? Write that as a matrix, okay? I'm going to get rid of some of my scratch work here. Okay, like this down here I don't need. Probably don't need much of the rest of it either, but I'm going to keep it because we did all that work to get it. What would be your matrix? 1, 1, 0, 0, 0, 20. Okay. Thought he was going to get stuck on zeros there. Okay, next. 0, 0, 1, negative 1. How about that 0, negative 20? All right. Not a lot of room there, but it was there. Okay, next. 0, negative 1, negative 1, 0, 0, negative 20. Next. 1, 0, 0, 0, and negative 1. Okay. Negative 10. Lastly, three zeros, negative 1, 1, negative 10. Got it. Good deal, folks. Everybody agree? What's really nice about this one? Ones and zeros. What does it remind you of? Computer signals, right? Plus 1. Everything in a computer either a 1 or a 0. So, but that's really nice here. Okay, really, really nice. Okay, that plus and minus 1 and 0. They're not quite a computer system, but still. Anyone ever heard of an electrical circuit? What do they call those? Controllers. There's a variety of names of things that, you know, deciding what gates open, close, that kind of stuff. They have a bigger name for it. I don't remember what it was, but electronics people would take that. What do we want to happen first in this set of equations? Leading non-zero entry of the first one of 1. Guess what? We got it. Good. What do we want to happen next? There, you want that to be a 0. Done. That to be a 0. Done. Well, you want that to be a 0. How are we going to make that happen? Negative row 1 plus row 4. Okay? Now, this is going to be a lot of writing, folks, but it's real simple writing. unless you tend to make errors when you write, and then you could be in deep doo-doo, trouble. Okay, that would be what? 1, you just write it down. The first equation, the first row, you're just using, you're not changing, so write it down. 0, 0, 0, 20. Not doing anything second row, write it down. 0, 0, 1, minus, that's where your problems come, folks, is keeping neatness, keeping your ledger in order. 1, minus 1, 0, negative 20. Next one. Can I go on and change that next one? I don't like writing all those negatives down. Can I change that at the same time? Minus row 3. Okay? I'm going to write that as 0, 1, 1, 0, 0, 20. Do you mind if I do that? I just don't like having to write extra minuses. They get in my way. Okay, but we're operating on row 4. What is that going to be now? 0, negative 1, 0, 0, negative 1, second, negative 30. Very good. All right. And that next row, I kind of don't like that. I'm going to do negative row 5 too. Is that all right? 0, 0, 0, 1, minus 1, 10. I just don't like leading negatives. I just don't like them, But, well, I might not should have done that, but I did it. It's okay. It's a legal move, right? Okay. Next. Let's review what we got. Leading 1 here, 0 is below it. Done. What do we want next? We need to exchange those 2 rows because I want the next leading one, non-zero entry to be a 1, which is fine. But then you have that here too. That's not stepping down. So that's not row echelon form. And certainly not reduced row echelon form. We want that up here. So let's swap these 2 rows. That's one of the reasons I did the other thing. So let's do row 2 interchange with row 3. All right, which means writing all this over again, which takes all the time. But you're not messing with row 1, write it down. 1, 1, 0, 0, 0, 20. Okay, the new row 2 is, tell me, 0, 1, 1, 0, 0, 20. New row 3 is 0, 0, 1, minus 1, 0, negative 20. Okay, and now this minus 1 I'm not going to change because it's not going to wind up being a leading 1. So I'm going to leave that one alone, okay? 0, minus 1, 0, 0, minus 1, minus 30. I know it seems crazy to have all those minuses there, but I think it'll actually help. Next, 0, 0, 0, 1, minus 1, 10. Okay. Now, don't know which is more important, the original drawing or is it time? How sad you bring me such bad news. What I'm going to say is take this home and finish it. Okay? If you can't get it, bring it back and we'll figure out what went wrong. Okay? So that'll be it. We'll start next time on and basically the next page starts with Kirchhoff's law. So we'll begin basically on that page. Okay? And on page 30. Did we do enough to do so? Oh, look at 1.3 is a really short section. If you want to try some polynomial curve fitting, you can. We didn't do any actually in class, but if you want to give it a shot, any of the odds 1 through 11 would do. Okay?
Then they have a couple of other non-polynomial functions that you can also do if you want to try those, 13 or 15. There's a population problem, 17, which is a scaling issue. You don't have to do any of these because we skipped them kind of, but if you want to, you could, just if that's of interest to you. Net profit would be another scaling problem. That's number 19. There's a guided proof if you want to do that, still dealing with the polynomials, so you don't have to do that. 23 is leading to a calculus situation. I'll let you decide whether you want to do that or not. 25, again, is a graph of a point, so a nonlinear thing. Number 27 is the first network. So if you want to start working on some of those, 27 and or 29, you might want to try, well, we haven't done Kirchhoff's law, so just 21, 27 or 29. If you want to do some of the previous ones just for practice and for fun, go for it. I won't want to stop you. Good deal. We'll see you Wednesday. Good class, folks. Sorry that Emmanuel got long-winded there and we went over, but